One key concept with simple harmonic motion, and especially to do with Hooke's law, is this thing called the Young modulus. Now, you might not see the word anywhere here on this slide, but that's because we need to have two sort of prerequisites before diving straight in. So when we apply a force onto a spring, we're essentially just creating mini forces, because we can't necessarily create one direct force. There's actually going to be a bunch of tiny forces acting on the spring. So if we sort of take like a side-on view, if we try to pull directly on the middle of the spring, what we're actually going to see is that there's just a bunch of these mini forces acting on it as well. Instead of just one continuous force. Now, this is essentially, along the base of the spring, the force divided by the area, which you may recognize soon as pressure, or how you recognize pressure. But in a case of this, we call this the stress applied to the object. So this is stress, and it's this formula here. Sigma is F divided by A, although I should actually say that it's the sum of the forces, sum of the vector forces. So it's essentially the sum of the vector forces, and the units are newtons per meter squared, sometimes called a Pascal. Now the strain is essentially just how far it's been stretched, simply. So it's dimensionless and is given this formula here. Epsilon is the change in length over L0, where L0 is the natural length. So if no forces were to be applied, how long would the spring be? So with that knowledge, we can now get to the Young modulus, which is essentially the ratio of stress to strain, and it is a bit of a wacky formula. So we have that E is sigma divided by epsilon. Now, the way we get this is because we have force divided by area divided by the change in length over L0, and because division flips, we end up getting that's FL0 over A delta L, which is how we get this. Now, there is a key thing to note, and it's a bit complex, so you can move on to the example after this if you wish, or you can move on now. But the way we're considering the forces is something known as a uniaxial force. So a uniaxial force is one that occurs along one plane of action. So if we have, again, the side-on view of the spring, what we're essentially considering is if we pull here, then we're only considering forces along this line of action. So if we suddenly pull the string outward, this is going to have two axes to consider, and we're going to assume that it's a 2D spring, which it clearly isn't. But if we just consider two axes as normal, sort of like this, then if we take this vector here, which I actually should have done in a different color. So if we're considering this force here, the green box is the plane that all of the forces must lie on, and of course a plane being an infinitely thin surface. Whereas with this one, we actually only we need to consider all of them occurring along this blue plane that would continue out forever. So when considering Young modulus calculations, we need to think of a plane which sort of, I guess, benefits both of these. And so we're not going to cover this. We're just going to assume that everything's uniaxial. But we can sort of do like an angled bisector and consider this plane. However, that's where things get a slight bit complicated. And we're just going to leave it out for now. However, you are free to sort of mess around with doing this. And with 2D springs, this sort of thing is considered a biaxial force and not a uniaxial. So there's the thing to look up if you're entirely interested.